Hi everyone, this is Scan 121 week number 11, and today we'll be talking about matrices, just going over some of the matrix math which you should have taken or should be taking at the moment in your elementary calculus or math classes, or maybe you took it before. And we'll do some basic Python operations, or go over the Python instructions on how to do these matrix operations. So let's start off with a quick review of what a vector is. So if you remember, a vector is a point which you can refer to using two components, right? Or maybe more than two components. It's a point which you can reference using a bunch of dimensions. So in this case, I have a vector called v, and I'm referring to it using dimensions x1 and x2. So if you look at the figure here on the right-hand side, v is actually this point right here, right? Let me bring this guy here. So this is v, it's the point right here, and you usually connect it to your origin, which is the 0, 0 point. And then this point, refer to it using its coordinates, right? So I have x1 is the x coordinates, x2 is the y coordinate. And when I basically locate it on the grid, here it is, v connected to the origin, this is my vector. And vectors are important in engineering because, a lot of the time, the things we refer to are not only numbers, they usually have a direction. So for example, you have fluid going through a pipe, this fluid has a direction. You're designing, some operation, a mixing operation, a separation operation, a reaction operation. A lot of the time, the transport phenomena at the different scales are governed by the direction of the flow, direction of the transport, etc. So understanding the concept of vectors is important. Sometimes you have vectors in 3 dimensions, so I might have vector x1, x2, x3, or it might be x, y, z. Sometimes it's I, j, k, whatever it is, the same idea applies, right? A vector is just a point in space which you can refer to using three or more dimensions. Usually 2 or 3 is what we deal with in engineering. And once you connect this point in space to the origin, you have a vector, which is a straight line pointing in that direction. Sometimes you can draw a vector from this point to another point. In this case, I have my second point, I have my other set of coordinates, and then I can subtract this vector from this vector to get the direction to the origin. Okay, hopefully this is not new. If it is new to you, or if you're having a hard time seeing this concept, please come to office hours and we can really go over it in details. But you should have covered this in math. Maybe go over your math lectures, take a look back on maybe some of your math books, early calculus books, and you should see this stuff. Okay, moving on to the second line, to calculate the magnitude of a vector. So a magnitude of a vector basically refers to how long this line is, right? So I can connect a point, or I can define a vector at any point in space. So maybe I can define a vector at this point, or at this point, maybe at this point, at this point. And it's also important to understand the magnitude or the length of this line. So how long is this line? I know this line, I have to go x1 distance in this direction, x2 distance in this direction. Sure, but how long is this line in itself? And you get this length using this equation. It's basically Pythagoras theorem, if you guys recall. So the magnitude of this vector v is the square root of x1 squared plus x2 squared. It's the equivalent of finding the length of the hypotenuse of a right triangle, right? Okay. If v equals 1, so if the magnitude of this vector is 1, it's usually referred to as a unit vector, right? Unit vector basically means a vector whose length is equal to 1. And v equals 1, most of the time we're referring to x1 is 1, x2 is 1, and you get 1. Sometimes it could be some other combinations. However, we're typically a unit vector refers to a 1, 1. Okay, the orientational vector, or this angle, again, it's simple geometry. Theta is basically tangent of x2 over x1. If you remember SOHCAHTOA for determining these angles. So sine theta will be opposite over hypotenuse. Cosine theta will be adjacent over hypotenuse. Tangent theta will be opposite over adjacent, right? So opposite will be this edge right here, which is x2, right? x2, this edge, and adjacent will be this edge right here, which is x1. So this is the basic idea of a vector. Moving on, you can always add and subtract vectors, right? So if I have two vectors v and w, the vector v has dimensions of x1 and x2, and the vector w has dimensions of y1 and y2. If I want to add these two vectors together, I need to add each component to its equivalent in the other vector, right? So x1 here can only be added to y1, so the sum will be x1 plus y1, and x2 can only be added to y2, and the sum will be x2 plus y2, right? And the same idea applies for vector subtraction. So if I want to subtract v from w, again, I do it element by element. X1 can only be subtracted from y1, so x1 minus y1, and x2 is subtracted from y2, x2 minus y2. Okay, so adding and subtracting vectors, the idea is simple. If you know that the vector has, a bunch of coordinates, so x1, x2, x3, and another vector w has a bunch of other coordinates, y1, y2, y3, if I want to add them, I just add the components in the I direction or the components in the first direction plus by themselves separately, and then components in the j direction or in the second direction separately, and then the components in the k direction or in the third direction separately, right? So you don't mix directions, you don't mix coordinates, you have to separate them. If you want to multiply a scalar by vector, so a is a scalar. Again, a scalar is just a number which does not have a direction, which does not have coordinates. For example, number 3. Multiply the number 3 by v is just equal to the number itself, the scalar, multiplied by the elements of the vector, right? So a into x1, x2 is equal to ax1, ax2, okay? And this is an exercise to go over for you to just try to refresh or maybe remember these ideas. You can recreate it in Python by yourselves to practice and recall some of the previous stuff we did. But basically, if I have a matrix, and now a matrix is a combination of vectors put together, right? So let's say I have a matrix here, 2, 5, 3, 1, and this matrix could refer to two vectors, put in two columns next to each other, or two vectors put in two rows next to each other. But usually use the idea of a matrix to combine, a list of numbers or a bunch of vectors together. And adding and subtracting matrices is the same as adding and subtracting vectors. So let's say I have this matrix right here, 2, 5, 3, 1, and I'm adding it to the second matrix here, 6, 2, 1, 5. So when adding these two matrices, you always do the addition is always element by element. So the element in this position can only be added in the element in this position. 2 plus 6 will give me 8. The element in this position, 5 plus 2 will give me 7. Element in this position, 3 plus 1 will give me 4. And then the element in this position, 1 plus 5 will give me 6, right? So you need to add every element to its equivalent in the other matrix. So you cannot just mix and match elements at different positions. So just be careful with this. And a lot of the time when doing matrix calculations by hand, it's a matter of being organized, especially if these matrices get big, or as we're going to cover before the end of the semester, how to use matrices to solve systems of linear equations, differential equations, You can use matrices to solve all these systems of equations. But the idea is basically it's element by element. You have to know how to deal with it when doing additions, subtractions, and multiplications, which we'll get to it in a bit. Okay, let's move on to the second idea here, which is the dot product of two matrices. So let's say I have two matrices in space, V and W. V has coordinates x1 and x2. W has coordinates y1 and y2. And we want to determine the dot product of these two matrices, or these two vectors, sorry. So dot product is a specific type of operation, and usually V dot W. And as you can see here in the dot product, I'm doing is I'm multiplying element by element. So in this case, the dot product of V and W will be x1 multiplied by y1, which is the element in the first position in the vector V, multiplied by the element in the first position of the vector W, plus x2 multiplied by y2, which is the element in the first position in the vector V, sorry, the element in the second position in the vector V, multiplied by the element in the second position in the vector W, right? So V dot W will give me x1, y1 plus x2, y2. And one thing to remember about the dot product is that this number is a scalar. It does not have a direction. I no longer have I and j. I no longer have these brackets to indicate coordinates. This is just one number. And comparing it to addition and subtraction, so if I just go back up quickly, when adding and subtracting vectors, I still end up with a vector, right? So V plus W here, x1 plus y1 in the first coordinate, x2 plus y2 in the second coordinate. The final answer is still a vector, right? So still this final answer still has a first coordinate, second coordinate, an I and a j, x and a y, whatever it is, still has two coordinates. Unlike a dot product, the answer is a scalar, right? So it's just x1, y1 plus x2, y2. And this is very important to remember. Try not to forget this here, that the product or the dot product will give you a scalar. Again, it's written here, it will give you a scalar. Alternatively, this is one way to do it. Another way to do it, which you might see as well, V dot W, is to magnitude of V multiplied by the magnitude of W multiplied by cosine alpha, which is the angle between them, right? So sometimes you don't have these coordinates, however, you have the magnitudes and the angle between them. You can use this operation to get the dot product as well. So dot product, you can get it using two ways. First way is just element by element multiplication to get the scalar. So V has coordinates x1, x2. W has coordinates y1, y2. To get the dot product, I go x1, y1 plus x2, y2. Alternatively, I could just multiply the magnitude of V by the magnitude of W by the angle between them, which is cosine alpha in this case. And the magnitude, the way to calculate the magnitude, as we mentioned previously, to get the magnitude of a vector, it's just square root of x1 squared plus x2 squared, square root of the first dimension squared plus the second dimension squared plus the third dimension squared if you have a third dimension. This is how you get the magnitude of vector. Okay. And then there's one final note here. If V is perpendicular to W, the dot product is 0. And the reason for this is, cosine 90 is 0, right? So V dot W cosine 90, and this is 0. So if these two are perpendicular, so if the vectors look like this, this is V, and this is W here, this is V, this is W. The dot product of these two guys is 0. Okay, this is the idea for dot product. Please, have a look at it, think about it. If it's not clear, come to office hours, send me an email. We can talk in details about this idea. Okay, moving on to the cross product. And again, a cross product is also another type of operation in vector math. And if I have two vectors, again, we're talking about v and w. W, v, when I do the cross product between these two vectors, I get a third vector, which is perpendicular to them. Okay, so it might be hard to visualize, but v and w are on the same plane, and then u is on a perpendicular plane to v and w. Okay, so you can imagine, you know, let's see if we could. So u is perpendicular to v and w in this way. So if v and w are flat on this page, u will be pointing towards your face. Okay, and this is the cross product basically. If I have two vectors v and w and I cross product them, I get another vector which is perpendicular to them. Okay, and to get the value of, and this cross product is always a vector, so this is important to remember. Unlike the dot product, which gives you a scalar answer, a cross product will give you a vector answer. Okay, so what's the magnitude of this cross product? It's equal to magnitude of v, the magnitude of w, sine alpha, right? So this is how you get the cross product. VW sine alpha will give you the cross product, and the direction of the cross product again is perpendicular to v and w. Okay, so you're gonna get a vector with this magnitude, which is VW sine alpha, and the direction perpendicular to these two vectors which you are crossing. And the orientation of u, so the orientation of this cross product, u will be perpendicular to v, right? And u will also be perpendicular to w. So this vector u here, which is a cross product of w and v, is perpendicular to both w and v. Okay, and if v is parallel to w, so if these two vectors here are parallel, you cannot cross product them because they don't cross, basically. Okay, good. And this is this is just some basic coordinate systems for you to have a look at. So usually when you have a vector, you refer to the element in the first position as I, the element in the second position as J, and the element in the third position as K. And I, J, and K are unit vectors. So as you can see here, these three have dimensions of, or magnitudes of 1, sorry. And, because J times K will give me I, as J and K are perpendicular, K times I will give me J, and I times J will give me K. And this is the cross product of these three unit vectors because they're all perpendicular. But basically what the IJK system does is, let's go back here. So we usually refer to the vector V as x1, x2 in brackets. If you don't want to do this, you can always say, x1 I plus x2 J, right? Here we go. And this is what the IJ system does. So in case you don't want to use the brackets to represent the vectors, you can always say IJ, and it's sort of a standard to understand that I is the first element or the X direction, J is the second element, which is the Y direction, and then you have K, which is the third element in the Z direction. Okay, and then continuing the idea of a cross product here. As we said, cross product, I'm crossing two vectors. I get a third vector with this magnitude, V, W sine alpha, and the direction is always perpendicular to these two vectors. So in case you want to get the exact elements of the cross product, you can always use this formula, right? So if I'm crossing two vectors, V cross W, to get the cross product U, V has coordinates of x1, x2, x3. W has coordinates of y1, y2, y3. If I want to get the cross product, this is the formula to use, right? So U is the cross product, will have three dimensions, as we said, or three elements. The I here, the J, and the K, right? Sorry, the I, J, K. And the element in the I direction, or the I element, or the first element, first component, will be x2, y3 minus x3, y2. Second one, x3, y1 minus x1, y3. Third one, x1, y2 minus x2, y1. Just plug in the numbers into this formula, and you get the cross product of these two vectors. Good. So let's move on to matrices now. A couple of pages ago, we had an example of matrix addition. So now let's talk about matrix multiplication. Okay. Let's say I have two matrices, A with dimensions of n and m. So I have n rows and m columns, right? I start with A11, end up with A and m. In Python, as we said, we start with 0, 0. So we're going to start with A00 and end here at A n minus 1, m minus 1. But you know, the same idea applies, you're just subtracting one. And I'm multiplying this vector A by a second vector B with dimensions m and p. So this vector B here has m rows and p columns, right? So B11 all the way to BMP. So if I multiply these two vectors, I get if I multiply these two matrices, I get a third matrix C with dimensions n by p. And it's very important to note the dimensions of the product n by p, because it's equal to n here and p here, right? So n is the number of rows of the first matrix, and p is the number of columns of the second matrix. And when someone tells you, I don't know if you heard this before, but usually when doing matrix math, someone tells you inner dimensions must agree, right? And this is what they mean here. The m here has to match the m here, right? So the number of columns in the first matrix has to match the number of rows in the second matrix. Otherwise, you cannot multiply these two matrices. That's what, I mean, it's common usually if you're doing MATLAB. I think Python also gives you the same error. It tells you inner dimensions do not agree. This is what this means, right? So if I'm multiplying these two matrices, A and B, I'm going to get a third matrix C with dimensions n and p, which are the outer dimensions here, and the inner dimensions must agree. So as you can see here, C and n times p is equal to A, n times m, b, m times p. Okay, and A and B must have compatible dimensions. This is very important, otherwise you can't do anything. You can't multiply them. It's just not going to work. Okay, so this is just the basic principle. So how do I actually multiply two matrices to get a third matrix? Okay, Cij, so the element, so C, so we said C is a matrix with dimensions n and p, right? So you already know C. It has n rows, right? And p columns. Sorry about that. P columns. N rows and p columns, right? This is your product of this matrix multiplication. So how do we place the how do we place the elements in each? Sorry, how to determine each element in this matrix C? Use this formula, right? Cij is equal to Aik multiplied by Bkj. And this looks, I mean, you can do it hand by hand and really trace these types of, trace the reference letters of each matrix. But the basic idea is that I'm multiplying row by column. You should always remember this. You are multiplying rows by columns. And this idea is very important, multiplying rows by columns. So if you have a matrix C, the first element will be A11 multiplied by B11. Second element will be A12 multiplied by B21. Third element will be A13 multiplied by B31, etc. So you're multiplying rows by columns. Okay, and this is a very important idea to remember. So again, if I want to get C, C11, it will be equal to A11 by B11, right? So your first element in the matrix will be basically C11, okay? Second element of the matrix, which will be, let's say, C12, will be A12 multiplied by B21, okay? Again, it's very important to remember this. Third element will be A13 multiplied by B31, okay? And the reason for multiplying rows by columns is that the inner dimensions must agree, or the inner coordinate must agree. So I'm always multiplying A11 by B11, A12 by B21, right? The k's here have to match. A12 by B21 will give me a, so we said 1, 2, 2, 1 will give me, doesn't make sense, right? We said A12 by B21 will give me C11, okay? That's the basic idea. I think this formula is missing a -1 here, but generally this is the basic idea. Let me see if we can go through an example here for a second. Okay, so let's look at this example. I think this will make it easier to visualize this matrix multiplication. So again, let's say I have two matrices here. Let me zoom in a bit. Okay, so I have two matrices here. The first matrix, let's call it A, has elements A11, A21, A31, or A, here it's referring to just A2, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then a second matrix B here, B, 1 to 9. And when multiplying matrices, again, we said you're multiplying rows by columns. So I multiply the first row by the first column to get the first element here, which is C1. I multiply the second row by the first column to get C2, third row by first column to get C3, and then I go back again. First row by second column to get C4, second row by second column to get C5, sorry, first row by second column to get C5, and then first row by third column to get C6, and then do the same for the third row. Okay, let's have a look at an example here. So if I have two matrices A and B again, A is 1, 2, 3, 4, 5, 6. So the dimensions of A will be, 2 by 3. Dimensions of B will be 3 by 2. So their inner dimensions agree. So we can multiply them. In order to get the product of these two matrices, sorry, or A multiplied by B, I multiply the first row by the first column to get the first element here. So let's have a look here. So I have 1 multiplied by 6, 2 multiplied by 5, 3 multiplied by 4, right? This is the first row and the first column. When I multiply these two guys, or these two vectors, basically I get the sum, or get the dot product of them, right? And so I have 1 times 6 plus 2 times 5 plus 3 times 4, and I get the first element here in C1. Okay, to get the element here in, C2, I go 1 multiplied by 3 plus 2 multiplied by 2 plus 3 multiplied by 1, and I get this element here. To get the element here, I go 4 multiplied by 6 plus 5 multiplied by 5 plus 6 multiplied by 4. I get this element here, and then finally to get the last element is 4 times 3, 5 times 2, 6 times 1, right? Row by column to get each representative element. Just be careful, when, let's go back to the body here. When referring to the components using the i's and j's. Just be careful, you know. It's sometimes hard to visualize. You know, a second ago I just confused them, and you know, sometimes it's hard to keep track when doing it manually, and it becomes even harder when you're just looking at a script. If you don't verify the numbers by hand, or if you don't have an idea of the type of answer you should expect to get. Okay, so just be careful about these things. But the basic idea is that, as we said, you multiply rows by columns. Okay, and you'll need to practice it a bunch of times. Maybe you haven't done it before. Hopefully you've done it in your elementary calculus classes, but if you haven't done it before, just try to practice it a few times. Maybe generate a bunch of matrices and multiply them until it's sort of, you know, until you get used to it, really. It's not a complex idea. You just need to get used to it or get comfortable with it, right? So here I have, again, I have two matrices, 1, 2, 3, 4, 5, 6. And the second matrix B, 6, 5, 4, 3, 2, 1, the inner dimensions must agree. So basically, this is, we said it's 2 by 3, this is 3 by 2. The inner dimensions must agree. So when I'm multiplying row by column, first row by first column here, I get 1 times 6 plus 2 times 5 plus 3 times 4 to get the first element. To get the second element here, again, I multiply the first row by the second column. So I have 1 by 3, 2 by 2, 3 by 1. And then I move on to the second row to get the third element here. Again, second row by first column, 4 by 6, 5 by 5, 6 by 4. And then to get the last element here, I multiply the second row by the second column, which is 4 by 3, 5 by 2, 6 by 1. Okay? Row multiplied by column. You keep multiplying the first row by each column until you're done with the columns, and then you move on to the second row, multiply them by the columns until you're done with the columns. Okay? Idea is you just need to practice until you're comfortable with the routine. Okay, and as we said before, A and B must have compatible dimensions, and you know, the order of multiplication is important, right? So A multiplied by B is not equal to B multiplied by A. So assuming they all have the same dimensions, so let's say A is NN and B is NN, multiplying A by B is not equal to multiplying B by A, right? The order is going to change of your C components. Okay, let's move on to another idea called the transpose here. And when transposing a matrix, I'm just flipping the rows and the columns. And this is sort of a manipulation tool for you to use, because sometimes you want to multiply two matrices, but you know the dimensions don't agree. But you know, from a physical perspective, from an engineering perspective, this is what you want to do because you want to multiply the information here by information there, whatever. You do a transpose to do this for you. Let me go back to the PDF. So we're looking at the transpose here. So by definition, C of M by N is equal to the transpose matrix A of N by M. So I'm just flipping the rows and the columns. Okay, so idea of transpose, very simple. So if you have a matrix which is one row, it just becomes one column. If you have this matrix which is, you know, N by M, you take transpose, becomes M by N. Here is M by P, becomes P by M. So transpose just flips your matrix, flips the rows and columns. Okay, matrix determinant, and the matrix determinant is an important idea. It's used a lot in differential calculus when solving differential equations. I don't know if you end up being a petroleum engineer. I don't know. They like using these types of numbers a lot. But anyways, so matrix determinant is basically, yeah. So the determinant of one element is the element itself. So you can't really take a determinant of a single element. Determinant of a matrix which has 4 elements, let's say A11, A12, A21, A22, is equal to can see I'm just multiplying the elements along this diagonal, right? So A11 but multiplied by A22 minus the elements along this diagonal, which is A12 multiplied by A21. And this is called the determinant. This is a scalar, it's just a single number. And this is referred to as the determinant of a matrix, okay? And usually when doing a determinant of a matrix, it's the easiest way is to just know the formula and just do it. Once you get comfortable with it, you can start, trying to realize the trend, or the basic idea or the basic trend of the generating a determinant. So let's say I have a slightly bigger matrix here. It's a 3 by 3 matrix, and I'm trying to get the determinant. Okay. So to get the determinant, you see I have A11, A22, A33, which is the product of the elements along this diagonal. And then I have A12 multiplied by A23 multiplied by A31, which is the elements along, the second diagonal, starting on the third diagonal, or it's the equivalent of me placing two matrices next to each other and just taking the diagonal along them, right? Maybe it becomes easier if we do some rearranging here. Let's go back here to the Word document. Let's have a look here. Okay, let's see if we can do this. Crop this guy a bit. Okay, so if I want to take the determinant of a 3 by 3 matrix, as you can see, I'm taking the elements along the first diagonal, which is A11, A22, A33, plus the elements along this diagonal here, which is A12, A23, A31. So the easiest way is to just write it twice next to each other, and it becomes this diagonal plus this diagonal plus this diagonal here, A13, A21, A32, minus the diagonals along the other dimension, which is A13, A22, A31, sorry, minus A23, A32, A11. If you want to visualize the minus as well, you just put another matrix under it, right? So in this case, it becomes A13, A22, A31, A23, A32, A11, A33, A12, A21, and you just add these components, subtract these components, and you get your matrix determinant. Okay. And again, this is a thing we just practice it a few times, get comfortable with it, and then it will make sense, all right? Or you'll get used to it. Basically, the concept is not difficult. Just basic multiplication, addition, just dealing with the arrangement and dealing with the coordinates. This is really the big issue with vectors, right? Just getting your head around all these coordinates and not confusing. Good. Let's move on. Matrix inverse. A matrix inverse is so if I have I think it's easier to avoid this definition. Basically, a matrix inverse does not exist, but it's necessary, it's sufficient condition to get a square matrix, okay? So if I have a matrix A multiplied by the inverse, I get a unit vector, okay? So A inverse is just A11, A12, A21, A21 minus 1. This is the notation to refer to an inverse matrix. Just write the matrix and you have a minus 1 in the top right corner. And the way to determine the value of this inverse, use this equation, or this sort of, what do you call it? This form factor, right? Or this form. It's 1 over determinant of A multiplied by this rearrangement of these components. So it's A21 minus A12 minus A21 A11, and you're gonna get the inverse of a matrix. Okay. So again, to get an inverse, this is how you do it. So if I have a square matrix A, which is A11, A12, A21, A22, and I want to get the inverse of it, I multiply 1 over the determinant of matrix A by the rearranged matrix A. So 1 over determinant, we just went over how to get the determinant, right? It's diagonals. And then rearrange, basically, I rewrite it. So this was A11, A12, A21, A22, becomes A22 minus A12 minus A21, A11. This is how you get the matrix inverse. Revise this idea as well. It's important in vector math. Okay, I think this is the last idea, eigenvalues and eigenvectors. Hopefully you've covered this in your calculus course. If you haven't, it's fine. You might end up covering it in some of your chemical engineering courses, I'm not sure. But basically, let's have a look here. You have an eigenvalue lambda and eigenvector u, okay? And the eigenvalue and the eigenvector satisfy the following correlation. A, which is a matrix multiplied by u, is equal to lambda multiplied by u, where A is a square matrix. Okay, this is the definition. The idea might seem out of nowhere, but this is what an eigenvalue and eigenvector is. We use this idea to solve systems of differential equations. Once you take your differential equations course, hopefully you'll use this. If you take an advanced process control course, if you end up going to graduate school, this is how they do it to deal with control systems, which are a bit more complex. We do this to deal with transport phenomena, which are a bit more complex. Petroleum engineers deal with this a lot to solve, flow and porous materials and this and that, etc. But anyways, for the purposes of this course, just know that, understand the basic idea, that multiplying u by a scales u by lambda. So basically, I'm multiplying a vector u by a square matrix, and this has to be equal to a value, an eigenvalue lambda, multiplied by the same vector u. And what this operation does is that it scales u by the eigenvalue lambda, right? And if you rearrange it, so if I rearrange this, guys, so if I have au minus lambda u is equal to 0, I take u out, factor it out, so I get a minus lambda I u is equal to 0. And this has a solution. So this equation only has a solution if the determinant is equal to 0, right? Eigenvalues are the roots of this determinant, which is polynomial in lambda. And if you substitute the resulting eigenvalue back into au equals lambda u and solve, we're going to obtain the corresponding eigenvector. Okay, so if you haven't covered this in your differential equations course, don't worry about it too much. I'm just introducing the idea for you. Eigenvalues and eigenvectors, just know the basic idea. These are just two numbers which I use to solve a system, or a rearranged system of equations. A usually placed in A, right? And A, we're gonna see how we're gonna rearrange a system of equations in this format next lecture. But use eigenvalues and eigenvectors to solve this system of equations, or to solve this vector, so solve this matrix system, etc. So for the purposes of this course, you just know that this exists. I don't expect you to be very good at it, or I don't expect you to be proficient at it, or even attempt it in this course. This is for other math courses to deal with. However, I do expect you to be comfortable with all of these matrix operations. You should be able to multiply matrices, should know what a transpose is and know what an inverse is, should be able to get the determinant, cross product, dot product, adding and subtracting, you 100% should know. If any of these concepts you're not comfortable with, please come to office hours. Let's talk. Let's go through them slowly. Okay, so now let's go to the Python. Let's see what should we do in Python. So what I want you to do in Python is just recreate these operations in Python. See how do we do all of these sort of matrix operations in Python. And the way we're going to do it, we're going to create two matrices, M and V, right? So first of all, we're going to import NumPy as NP. M is equal to NP array, so I'm creating a matrix, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I'm creating a vector V, which is just 1, 2, 3. And we're going to get the dot product of M dot V, of V dot V, of the transpose of V multiplied by V, multiplying M and V and V, multiplying the matrices together, getting the transpose of M, getting the transpose of V. I'm determining, the shapes of these transpose. I'm getting the inverse of M. I'm getting the determinant of M. And this is how we get the eigenvalues and eigenvectors of M. Okay, and what I want you to do is I want you to submit your script, your comments on the above commands, what works, what does each command do, what doesn't work, and your scanned copy of your hand calculations of all of these operations, actually except the eigenvalues and eigenvectors, forget about it. But please do your hand calculations for all of these operations and submit it with your homework. This is due next Monday by, let's say next Tuesday by 11 a.m. Okay, let's do it this way. Good. So now let's move on to Python for a bit. Let's go through them one by one together and just see what how we're gonna do this. Okay. So first line here. Let me double check on sharing the screen. Good. So I'm gonna go import NumPy as NP, and this is important. We need to import the NumPy library to be able to do anything. M is equal to NP dot array, and I'm creating the first matrix. And again, to create a matrix, 1, 2, 3. So each row goes in its own set of square brackets, right? 4, 5, 6, and then 7, 8, 9. Okay. And then I'm gonna create a second vector here. V is equal to np dot array. Same idea applies. Each row has to go in its own set of square brackets, even if it's only one element, right? So if I run this, okay, it runs, and now let's present M. So here I'm looking at the bottom right. Actually, let me zoom this guy. Looking at the bottom right here, when I write M, I get my matrix here, 1, 2, 3, 4, 5, 6. Then when I write V, I get my, still a matrix, it's just one column. Okay, let's attempt some operations. There's a small error in the PDF tutorial, so just be aware of it. If I just write print, if I just follow the tutorial M dot V, you're gonna get an error, right? Tell you it's not happy, invalid syntax. What you need to do is, after the print, you need to put this in a second set of brackets, right? So if I put M dot V here as a second set of brackets, and I run it, I'm gonna get the dot product of these two matrices. Okay. And this is the dot product of these two matrices, and these three elements are scalar, right? So the answer is 14, 32, 50. These three elements are scalar. It's the equivalent of multiplying each matrix by, equivalent to multiplying each vector by its equivalent, right? So I have 1, 2, 3 multiplied by its equivalent here to get the number you want, okay? It's basically, 1 multiplied by 1, 2, so I'm gonna get 1. 2 multiplied by 2 is 4. So 1 plus 4 is 5. 3 multiplied by 3 is 9. 5 plus 9 is 14. This is your first element. 4, 5, 6, 7, 8, 9. It's basically the equivalent of multiplying the matrices. If you want to test it with a second vector, so if you want to create two vectors and multiply them, you can do that and you'll still get dot product as a scalar. So if you want to test it, I'm gonna create the W vector, from the lecture, and I go 10, 20, 30. And instead of doing this, I want to do W dot V. Yes, so in this case, the shapes are not lined because I'm multiplying them as matrices, as an array, as a matrix. But basically, you'll need to rearrange them as vectors and then multiply them, and then you're gonna get the answer. Anyways, for the purposes of this lecture, let's get this lecture. Let's start closing this lecture. So I'm gonna just add some descriptors. So here I'm gonna just write the dot product of M and V. Okay, this is the first one. Second one here, I go print V dot V. I'm attempting to get the dot product of V by itself. And in this case, if you try to attempt this, you're gonna get an error. It will tell you they're not aligned because, V is 1, 3. V is 1, 3, and V again is 1, 3. So the inner dimensions do not agree, right? So you cannot really multiply them because you're trying to multiply 1 by 3 by 1 by 3. You can see that these inner dimensions do not match. So you're gonna get an error always when trying to multiply a vector by itself or a matrix by itself, if it's not a square matrix, Okay, let's try to get around this. So let's go print. I'm gonna take the transpose of V dot T dot V, right? So if I take the transpose of this, I will get an answer. Okay, it's not happy with this. Let me just let's comment it and let's run this. There we go. So we're able to get, if I take the transpose, I'm gonna get an answer of V dot V, right? So let's add a comment here. The dot product of transverse V by V. Okay, 1 second. Okay. I'm just adding a comment so that the results, you can see it in the results. So, dot product of M and V, this is what we did. And then the dot product of transverse V by V will give me this. And again, the idea of taking a transverse of a vector is to sort of realign it so that you can able to do some manipulations with it, right? So if I go V dot T, you can see it's just 1, 2, 3, whereas V itself is 1, 2, 3, single row versus single column. I cannot multiply a single column by a single column because the inner dimensions do not agree. However, once I take a transpose, it becomes 1 row by 1 column, This way I can multiply them without any errors. Okay, let's go on to the other command. Print np dot multiply m comma v, right? Sorry, this has to be a comma, m comma v. And you can see that this I'm just multiplying m by v. Okay. One thing you need to remember when doing this commands is that in the document uploaded, we're missing these brackets. So if you just write it without these brackets, you're going to get an error. Make sure to put a set of brackets around every command before printing. And as part of your homework, I want you to just take a look at this command, multiply this element by element multiplication, and compare it to the first one, m.v. So what's the difference? Okay. Difference with m.v. Why am I getting different results? So dot product of m and v, I get 114, 32, 50. Whereas if I multiply them, I get this matrix here, 1, 2, 3, 8, 10, 12, 21, 24, 27. Okay, think about it and let me know your thoughts in the comments. Again, other command in your lab, np multiply. Again, I'm multiplying two matrices element by element. This time I'm multiplying v by v, element by element. So if I run this guy, I'm gonna get an element by element answer for v by v. Then I have a bunch of commands where we're taking the transpose. You can do these by themselves. I'm gonna move on to the shape. So the m.t.shape, what does this give you? Let's run this and see. So m.t.shape gives me the shape of the transpose matrix, right? If you recall, v.shape, v is 3 by 1. If I take v.t.shape, I'm gonna get 1 by 3, right? So it gives you the shape of the matrix. Okay, let's move on to the. Let me just comment these guys. I don't want to keep on seeing these results. Let's go on to the third from the last one. So I have print. This time I have np.len algebra.inverse of m. Okay. And as you can see, this will give you the inverse of the matrix M. If you recall the way to get the inverse, so if you go back to our lab here, the way to get the inverse was to follow this formula, right? That's why all the numbers we get are a bit weird or clunky, right? But this is how it is, right? So the inverse, you should always follow this formula to get. Let's go back to Python. So this command here allows you to get the inverse. And then I have one more command, print np dot algebra dot determinant of m, and this will give me the determinant of m. And again, we talked about how to get the determinant of m. You can have a look and see it. And the determinant is always a single number. So here I have a single number, it's a negative number, 9.5 times 10 to the minus 16, right? It's a very small number, almost zero. It's basically zero. But anyways, and the comment here is that, if you do this by hand and verify what you're gonna get and see, is this actually possible? Or does Python carry on residual error in the calculations? Because if you get the determinant and you find that the determinant is actually zero, then this inverse is not possible, right? Because you cannot divide by zero. So this means that there are scenarios or Python, or usually this is the case with a lot of computational tools, they have this residual error, and this is due to computer storage or some other artifacts which we don't necessarily care about. However, they affect your calculations, right? So instead of giving you a 0 and telling it is not possible, give you a very small number and give you very large numbers here. So as an engineer, when you look at these numbers, you can gauge, how is it I'm starting with 1, 2, 3, 4, 5, 6, ending up with 10 to the power 15. So this is probably wrong. Okay, anyways, moving on to the last one. Last one, the method to get the eigenvalues and eigenvectors. Just understand the methods. Don't try. I mean, if you're comfortable, you can verify it by hand. If you're not, then forget about it. But just know the method. Try to practice it 1 or 2 times in Python. Just in case, once you progress throughout your careers and you find yourself at some point in your life needing to find eigenvalues and eigenvectors, this is the way to do it. So at least you know that's possible, right? So I'm gonna print eigenvals and print eigen. So let's try this as well. And it should give us the eigenvalues and the eigenvectors of the system. Okay, so please attempt all of these commands, compare them to your hand calculations, comment on the results, reach out to me if you're unable to do any of them, you're having a hard time, and schedule office hours. Come to office hours. I don't see a lot of people coming to office hours. So if you need help, just come to office hours, send me an email, and we can go through it together. Okay, this is it for this week. Thank you very much, and I'll see you next week. Take care.